When we're talking about discrete probability distributions, we might as well go ahead and talk about a binomial probability distribution while we're at it. A discrete probability distribution is where the random variable x can take on any number of discrete values, 0 through 10, 1 through 6, but just the integers. With a binomial probability distribution, it's an either-or situation. The variable can only take on two values, and those are generally going to be considered either a success or a failure, more for just the sake of how to discuss which is which than because one of them has to necessarily be good and one of them has to be bad. As a matter of fact, what a success is a fairly arbitrary situation. If you're talking about how many girls are born out of X number of kids, then since you're talking about the number of girls, you would consider having a girl be a success. On the other hand, if you're discussing how many boys were born, then you would consider having a boy be a success. So that's what I mean by arbitrary. The characteristics of a binomial probability distribution would be, number one, there have to be an exact fixed number of trials. So it's not a case of we're going to roll these die until we get a 5. Instead, it's going to be, what are the chances of getting a 5 out of 8 rolls? Or it could be, what are the chances of getting a 5 out of 2 rolls? Now, 5 is just the X value. So you could have various probabilities there. Second characteristic is that the trials have to be independent. Now, in a case where you are, for instance, taking a survey of people or something, and you're not going to survey the same person more than once, as long as you have a sample size of less than 5% of the total population that could be involved, then the difference of taking out one person is going to make so little difference that you can treat this as independent. In other words, if there are 100 people in a group and you're going to interview 3 of them, then for n equals 3, that is less than 5% of 100. And frequently, you're talking about surveys where the population itself could be in the thousands. So there's no point in treating those as dependent. The third requirement is that there can only be 2 possible outcomes. And we already talked about that. That's what makes it binomial. So it could be true or false, yes or no, boy or girl. Now, the characteristic of the outcome is not what we're talking about as having a probability. The fourth requirement is that the probability of success has to be the same every time. And that actually mostly goes along with the trials being independent. There's a lot of notation we need to talk about. If S represents success, and F represents the failure. Then the probability of a success, we let be lowercase p, and the probability of failing would be lowercase q. And since there are only two possible outcomes, the success or the fail, p plus q has to be 1. In other words, the probability of success or failure has to add up to 100%. This also leads to, we can write this either as 1 minus Q, P equals Q, or 1 minus Q equals P. So if you know P, you automatically know Q. Just subtract P from 1. Other notation that we use in this, N is going to represent that fixed number of trials. X is going to be our random variable. So that could change from 1 minute to the next. We could be trying to find out when X is 5, or in a minute we could try to find out when X is less than or equal to 7. But the number of trials within this same discussion is not going to change. When we talk about P of X, we're talking about the probability of having exactly X successes. What else is involved? Mu, your mean in these, is going to be N times P. Your expected value is the number of trials times the probability of a success. That's the expected value of any success. So if you've got 100 trials and you're talking about the probability of having a girl, and you're rounding that off to 50%, then out of 100 trials, you would expect to have 50 girls, right? So that would be our mean. Sigma squared, the variance, is also very easy to calculate. It is N times P times Q. Or you could say it is the mean times the probability of failure, because this is actually the mean right here. And the standard deviation, therefore, is the square root of N times P times Q. So it's really easy to just do these in your calculator. So we're not going to be bothering to use StatCrunch to calculate any of these. However, we will use StatCrunch to determine the actual probabilities of a probability of X, P of X. If we want to, for instance, let's look at an example. If the probability of success, we won't even talk about what it might be. Let's say the probability of success for any particular thing is 0.35. So that's P. And we're talking about when N is, I don't know, 3. Let's say we've got a bag with green marbles and white marbles. And there are so many marbles in this bag that we're going to be pulling out less than 5%, so we don't have to worry about the probability changing. And we'll say that because of the ratio of the green to white marbles, the probability of getting a white marble, the probability of getting a white marble is 0.35. Then that means the probability of getting a not white marble, which would be a green marble, the probability of getting one that is not white, if it either has to be white or not white, then the probability that it won't be white is going to be 0.65. 1 minus 0.35. So 35% of the marbles are white and 65% of them are not white. In this case, that happens to be green. If we calculate the probability of getting a white and a white and a green, exactly a white and a green, we can use the multiplication rule to say, well, the probability of getting a white one is 35. The probability of getting a second white one is 35, because we've got hundreds of marbles in this. And the probability of then getting a green one, which is a not white one, would be 0.65. Now, this isn't the only way to get 2 whites and 1 green. But the probability of getting a white and then a green one and then a white, well, that's going to be 0.35 and then 0.65 and then 0.35. So that's going to be exactly the same, right? And the probability, the only other way we could get 2 whites and 1 green would be to pull the green one out first. So that would be 0.65 times 0.35 times 0.35. So to actually determine the probability of 2 white and 1 green, we have to take into account the number of ways that it's possible out of 3 balls that we're going to take out to get 2 white. So that would be 3 choose 2, right? Times, notice that every time we did this, there were 2 whites, 2.35s and 1.65. So that turns out to be 0.35 squared and 0.65 to the first. Well, it turns out that the formula for determining our probability is n choose x, where n is the number we're going to pull out, x is the number we're interested in out of the sample, number of successes. It's going to be times p, the probability of pulling out x, raised to the x. So the probability of choosing 2 resulted in 0.35 squared. The probability of choosing x is going to be the probability of x times raised to the power x. And then the rest of them, the probability is going to be q. And what's left, because the 2 exponents have to add up to the number of, well, whatever n is, this is going to be raised to the x minus, the n minus x. So this is the formula for calculating the probability of getting x successes out of n trials. This is the probability of x successes out of n trials. Now, while these formulas are pretty simple, This one can get a lot more complicated, and even though it's not that bad, we can actually use StatCrunch to do this really easily. Let's say we look at this problem. Based on a poll, 50% of adults believe in reincarnation. That's pretty high. Assume that 5 adults are randomly selected and find the indicated probability. Okay, what is the probability that exactly 4 of the selected adults believe in reincarnation? And let's talk about how to use this in StatCrunch. Notice there's nothing here that I can click on to just put this information into StatCrunch. If I hit question help in StatCrunch and pull up StatCrunch, and I'm going to pull these apart so that we can see both screens. In StatCrunch, I want to go to Stat, Calculator, Binomial. It's going to default to this. Notice we got the graph, we got an N and a P of X. So in this case, our probability is 0.5. It's going to come up originally as that. Our N is going to be 5. We have a sample size of 5 adults. The probability that exactly 4 of the adults believe in reincarnation would be the probability that X equals 4, and that is right here. So fix this, fix this. This will be determined by the question of the moment. So out of N equals out of 5 with a probability of 50%, the probability that we get exactly 4 is 0.15625. And when you enter that, make sure that you double check how many decimal places they want. That's what always gets me. So 3 decimal places here would be 0.156. Excellent. Next question. Let me clear this out of my scribbles. What is the probability that all of the selected adults believe in reincarnation? Okay, now we're still talking about a group of 5 with a 50% probability. All of them would be exactly 5, right? No more, no less, can't do more. So exactly 5 is going to be 0.03125. 3 decimal places would be 0.031. The probability that at least 4 of the selected adults believe in reincarnation. At least 4 would be either 4 or 5. And we could, since this is discrete, there are only exactly 4 or 5, no 4.5 matters. We could actually just add the number for 4 and the number for 5, which wouldn't be bad with just 2 of them, but it would get kind of tedious if it said at least 1, because that could be 1 or 2 or 3 or 4 or 5. So rather than adding all of those together, at least 4 would be 4 or more. So if I put greater than or equal to 4, I get 0.188 to 3 decimal places, 0.188. And if I rounded those 2 numbers up there together, I would actually be off by 1. I don't know if that would make a difference or not, but this was okay. And then they want to know what the, let's see, go ahead and look, the probability that if 5 adults are randomly selected, is for a significantly high number. 0.188 is not going to be significantly high. Remember, the probability has to be less than 5% to be significant. So the answer is no. No, because the probability that 4 or more believe incarnation is less than 5%. No. No, because the probability that 4 or more believe in reincarnation is greater than 5%. Yes. Very good. Let's look at the next one. Now, there's no need for me to close StatCrunch and start it up again each time, since I'm not downloading any information in. I don't have to worry about that. Okay, now this one just wants to know the mean and standard deviation. So I wouldn't even use StatCrunch. I would just take my calculator. Recall that the mean is going to be n times p, and the standard deviation is going to be the square root of npq. So we just go ahead, we're talking about the probability is 0.75. We're talking about a group of 26. So my expected value is 75% of 26. If there's a 75% probability that P has green pods, and I pull out a group of 26, my expectation is that 75% of the 26 are going to be green. And 75% times 26 is 19.5. Now it says to round this, put it as a decimal, do not round. So it's going to be 19.5. Now, of course, I can't have 19.5 green pods, but the math is what it is. For the standard deviation, I've got my 19.5. I'm going to multiply that times Q, and the complement of 75% is 25%. So I'm going to multiply this times 0.25. Then I'm going to take the square root of this. That turns out to be 1 decimal place, 2.2. Use the range rule of thumb. I'll let you do that. Values of P's or fewer are significantly low is going to be, of course, if it's less than U minus 2 sigma, and it's going to be significantly high when it's mu plus 2 sigma. So just take these numbers and work them out. And so here we've got another problem. We'll do one more. The probability of a randomly selected adult in one country being infected with a certain virus is 0.005. In tests for the virus, blood samples from 24 people are combined. What is the probability that the combined sample tests positive for the virus? Is it unlikely for such a combined sample to test positive? Notice that the combined sample tests positive if at least one person has the virus. At least one would be the probability that 1 was infected, or 2 were infected, or 3 were infected, or 4 were infected, all the way up to 24. So we definitely want to use the technology to do this. So let's come over here. Our group is going to consist of n is 24. Our probability is 0.005. we want to know the probability that at least one person, so X is greater than or equal to 1, and that turns out to be 0.113, 3 decimal places, 0.113. Is it unlikely for this to happen? No, because this isn't less than 5%. So working through these is pretty easy. Thank heavens for StatCrunch. Let me know if you have any trouble. I'll talk to you later.